So it's about the physical measures. So on physical measure, it's a measure, a ergodic measure with positive basing. Its basing has a positive limit measure. And there is a very well-known conjecture given by Palis. So that any system can be approximated by another one having only finitely many physical measures. And the basins cover further big measure subset. And this kind of measures, it was first studied by Sinan, Roy, and Bauer for the C2 hyperbolic attractor. But for more general situations, there are many more examples in history. And in particular, the Bonatti and Viana, they started this kind of physical measures for diffeomorphisms with most contracted center direction. So here is the definition. So we have a diffeomorphism, which is partial parabolic. That means we have two bundles. The tangent space splits in two bundles. And the one bundle is uniform expanding, and another bundle we don't know. So this is partial parabolic. And we say if it is most contracting, if on every center leaf, an unstable leaf, because you have the unstable bundle, it's integrable, we have unstable leaves. So in every unstable leaf, you can see hyperbolicity. What means hyperbolicity? So basically, we have unstable leaf. There exists some subset. The center stable exponent is negative. So here we should be noticed that here we cannot use the Palis theory, because Palis theory we need invariant measures. Here we don't have any measure up to now. So what we need here, we need the hyperbolic time and the Palis lemma. To use the hyperbolicity, this is very weak. We need to use the Palis lemma to get the stable manifold. So that's the reason why I call it most contracted in direction. It's not contracting, but you can see the hyperbolicity on every unstable leaf. Okay, and in fact, this stable leaf is not from the Palis theory, but it's absolutely continuous. This has been proved by in Bonatti and Viana, and later see the thesis of Ali Dazibi. Okay, so we have the unstable leaves, and the center stable direction, we can see some hyperbolicity, some part of hyperbolicity. So Bonatti and Viana use this to prove that F has only finitely many physical measures, and the basins cover further big measure subset. So this satisfies the Palis conjecture. And later, more important is that Martin Anderson proved that this phenomenon is robust. It's a C1 plus alpha robust. So you give one diffeomorphism, which is most contracting, then we have an open set of diffeomorphisms with most contracting certain direction. So this is a robust phenomenon. So now we have one motivation. So what does the physical measures look like? We have a robust phenomenon. We know that it has physical measures, but what does the physical measures look like? And how they vary with respect to the systems. So this is not for the Palis conjecture. So now for some special kind of systems, we know that it has physical measures. So how to study these physical measures? This is our first motivation. Okay, so here I will give one example for systems with most contracting. So here we have a torus, and we have a circle. So this is a skew product space. And we consider a C product map X data to be Gx and Hx data. So here we have Gx. So we suppose G is unorthogonal. And for Gx, here is a fixed point of G, and there is stable manifold and unstable manifold. So there is a heterokinetic intersection Q. So here we have two circles. This is circle of P, and this is circle of Q. So we assume over SP, we have one sink and one source. No, repeller and attractor. So they have the same manifold. They have the unstable manifold. So we have 4 points here. This is only skew product. So we have skew product with this geometric structure. So this system is most contracting. It's produced by me and Marcelo. And it's very important is that the center for the Asian is robust, absolutely continuous. So after any perturbation, this is different to the body preserving case. Yeah, for perturbation, not a skew product. So now we have one question. We know that it's most contracting. How many physical measures we have? What are the physical measures it looks like? And how it change respect to the perturbation? Because most contracting is open property. So we would like to know this kind of information. Okay, so this is our first motivation. And the second comes from the examples. So there is a long list of examples of differs with the most contracted same direction. The first example should go back to the Furstenberg's study of random matrices. So Furstenberg is trying to study the random matrices. For example, we have 2 matrices. A1 is hyperbolic. This is only one example. And A2 is an irrational rotation. So we have the probability P to choose the A1, and we have probability 1 minus P to choose A2. So the question is, finally, we get the Lyapunov burden is Z or not. And how the Furstenberg studied this kind of problems, he considered the projection map induced in the circle. So for this first matrix, we have a north-south map. So for the second matrices, we have irrational rotation. So now we have probability P to choose the first circle map and the probability 1 minus P to choose the second circle map. In fact, we can say if you have more expansion, so in the circle map, you have more contraction. Because here expanding more, all the vectors will convert to this space, this direction, and so here you can see the contraction. And in fact, Furstenberg showed that for this kind of systems, it's most contracting. It's for almost all the pairs, it's most contracting. So this is why Furstenberg can show that the Lyapunov burdens for these random matrices generally which are not vanishing. Yeah, but anyway, he used another language. And later is Bonatti Viana, they really give the definition of the most contracted in the 1905 and 1906, which is Manier's example. So you have 3-dimensional linear anosov, center you have contraction. On some small region, you get a bifurcation, get expansion. But outside the small regions, you still have the contraction. It's reasonable for us to believe that it's most contracting. And the latest kind of example, we will explain a little later. And there is Dog-Biot, generic perturbation of time 1 map of geodesic flow of surface with constant negative curvature. This perturbation is C2. And later, it's body-preserving partial parabolic diffeomorphism with negative synthesis burden, but the unstable foliation is minimum. This should be open and dense in the C1 topology for any C1 for any 3-dimensional partial parabolic body-preserving case. It's open dense in C1 topology. And the last is a recent example given by me and Marcelo and myself. It's a general partial parabolic skew product diffeomorphisms with 1-dimensional center direction. Example is exactly looks like this. So the second motivation for us is that we have a lot of examples. We are trying to build a theory for this large family of these examples. Okay, so now let's see this kind of example. So the kind of example is an example on the cylinder. It's a little complicated, but the basic is look like this. So the horizontal direction, you produce 3. Vertical direction, you don't have, you have a vertical center foliation. So it's a partial parabolic endomorphism. So, in fact, for this map, it has 2 physical measures. It's proved by Kahn, and the one is above, and another one is below. So I will draw this picture again. So the basic of mu1 basically looks like this. So you have 1, this is state manifold, 1 point, and here you have P2. This is state manifold LP2. So you have a physical measure on the above, another physical measure in the below. So here you have fixed point and another fixed point. This fixed point is a saddle, a stable manifold is a segment, and this is a saddle, stable manifold is another segment. So let's see the basin of these physical measures. For the basin of mu1, it looks like this. I use another 2 colors to write. Basin of mu1, basically, if you draw a picture, it looks like this. I will only draw 3 segments to explain to you. It can really go downstairs, quite near to the low boundaries, because so the basin is very dense. It's very dense. And the basin of another measure, upstairs, the downstairs, is also everywhere dense. The basin covers 4 Lyapunov subset. Okay, so why in particular I prefer to explain these examples, because this example after perturbation would be quite strange. So now let me show another perturbation. Here is vertical, center foliation is vertical. Now we change the derivative here a little bit more. We expand it a little bit more. So what does the picture looks like? It's proved by Kahn. We still have 2 physical measures. We still have, mu1 and mu2. But these basins change quite a lot. So you have this one, and this one, this one. Another basin is like this one. They twist from each other. So what does it mean? So you have these kind of lines. They never reach another direction. They never reach. So basically, we have 2 basins. They cover 4 Lyapunov subset. But for these lines, union over these lines with the bigger measure Z. So this is a foliation which is absolutely continuous respect, but not equivalent to Lyubich. So this is first such kind of example. So you can see here everything is coherence, very good. After perturbation, immediately everything changed quite a lot. So this is a new example of foliation which is not absolutely continuous. But it still has some absolute continuation. So we would like, for example, we would like to know what is the dynamics happen, what is the basin change. And another question, if we don't preserve the boundaries, because almost contract is a robust property. Here we see if we preserve the boundaries, we have 2 measures. Now question, if we don't preserve the boundaries, what does it look like? Okay. So now we enter to another topological object. So for partial hyperbolic diffeomorphism, so here now it has no any relation with physical measures. So a skeleton is a finite number of periodic points, which with special index What's index of center stable direction. And any unstable leaf intersect the stable manifold of the periodic points. So it's a U section. It intersects every unstable leaf. And in the end, there is no any heterocanonical intersection between these orbits. So, of course, a partial parabolic diffeomorphism, they may have no any skeleton. Why? Because it may have no periodic points. That maybe does not exist. Okay. But for these two pictures, we can say they do exist a skeleton. What is skeleton here? Skeleton of F here is P0 and P1 and P2. We have a skeleton. We can see here what's a skeleton. The skeleton is point A. Why? If the unstable manifold does not intersect the intersection, it should be here. Unstable, it should be here, but then go here and come back to here. So we always have a skeleton. So a set, if it only satisfies these first two properties, A and B, is called a U section because it causes any unstable leaf. And the U section is a robust property. This has been proved by Bonatti, Diaz, and Ures. And a minimal U section is a skeleton. Okay, so this is topological object. So now we would like to connect this topological object to ergodic theory. So first, any diffeomorphism with most contracted center, it has a skeleton. As I have shown, they always have some skeleton. And the second, let F be a diffeomorphism with the most contracted center. Suppose it has key skeletons. What do we can get? The first thing we know is that it has exactly the same number of physical measures. Okay. The second, the unstable closure or unstable leaf of the orbit is exactly the support of the measure. And the closure of stable manifold of these periodic points is the basic. So if you give me a map, you tell me, okay, it is the most contracting. So how can I know that how many physical measures in general may be very complicated? Because as we see, every basin is dense. If you take one point, do the calculation, maybe you always choosing the same basin because everywhere both are dense. So from the topological object, it's very easy for us to find finitely many siders, and we know that exactly the same number of physical measures, and we know where the support of the measure and where the basin of the measure. Okay, so now I will explain, because Martin Anderson proved that diffeomorphisms with the most contracting center is a robust property, and the number of physical measures may decrease. Or maybe the same. So when they will decrease, the number of physical measures decrease after perturbation if and only if we have a skeleton. Here we have a skeleton. There's the same number of physical measures. After perturbation, the skeleton may be not to be a skeleton anymore because maybe we get a heterocanonical intersection. So the only reason we lose a measure when we get a heterocanonical intersection between different elements of a skeleton. Okay. And we can also know if we don't lose a measure, the support of the physical measures and the basis of the physical measures vary in a low semi-continuous way because they are closure of the invariant manifolds. So now I will give an application of our result to Kant's example. So when we lose a measure, we have a skeleton, P1 and P2. So first case, if F only preserves the low boundaries, we do a perturbation here. We do a little perturbation here. What do we get? We get an intersection between the unstable manifold of P1 and the stable manifold of P2. We get an intersection. Just do a little perturbation here. So what's the skeleton now? It's only one element. It's P0. Oh, sorry, P0, P. I need to change it. No boundary, sorry. Yes. So we only have one physical measure below. We don't lose this measure. We lose the measure in the above. And what's the basis of the measure? The basis of the measure now covers the whole manifold. So we just do a little perturbation far away the support of the measures, and then we change everything. We lose the one measure, and the spacing explodes. So if we do another direction to perturbation below, preserve the above, you preserve the above boundaries, but you lose another measure. So why? Because you get a heterokinetic intersection between the periodic points. In the last scene, if you do perturbation above and below, if we do perturbation above and below, we get a heterokinetic intersection between two. So these 2 points are homokinetically related. So the support of the measure equal to the closure on the manifold to the homokinetic class. The support explodes easier. And in fact, maybe Lorenzo will like this. This is an example of explosion of homokinetic classes. We have 2 homokinetic classes, above and below. After little perturbation, everything mixed together. Yeah, since I don't have much time, I will give a very quick application for the stationary measures. So the stationary measures basically looks like this. This is the generalization of Furstenberg's work. So you give us 2 circle maps. And this is the probability P and the probability 1 minus P. So what's the stationary measure? Stationary measure looks like this. The mu equal to the P. This is the stationary measure, the definition. And the stationary measure spaces is compact and convex. Its extreme point is called ergodic. So we would like to know that how many ergodic stationary measures we have. For example, I give a special example like this one. How many stationary measures we have? So this stationary measure can be related to a skew product map. Here is a shift, like this is sigma 2, and the circle is a fiber. So we get a partial parabolic map. For partial parabolic map, a skew product, there is many work we know that it's most contracting, but for most contracting, we have already know that we have a skeleton structure, and by the skeleton structure, we can know the number of physical measures. So we may use this to connect the relation between stationary measures of the random difference of a circle and the U theta over F. So definition, and this relation between the random maps and the skew product maps. And what we finally get is like this. If we have if we have a random process, we have a map of the random difference, then we can get a skeleton, and we can exactly see how many physical stationary measures we have. So in this case, we have only one skeleton. So we know that there is only one stationary measure. And what the supported is, support is a positive orbit of the point under the semi-group, and which is minimum. And this can be preserved after perturbation. After perturbation, the number of stationary measures cannot increase. And you can follow the finite many skeletons to follow the orbit and know what the measure looks like. And finish, yeah.